Hello folks, this is your first video in Unit 8, which is on inference from means. In this video, I'm going to talk about just the general overview, the basics, because there's a couple of changes that happen when we're talking about means versus proportions, right? And then a little bit later in this unit, we'll get into confidence intervals and hypothesis tests, right? So we're going to follow a lot of the same procedures that you're used to, a lot of the same acronyms, right? There's just little changes that you have to keep track of when we're talking about means instead of proportions, okay? So let's go ahead and jump into it here. So I want you to think back to when we first talked about sampling distributions for means, okay? Right? That was a little while ago, okay? But if you recall, right, the mean of the sampling distribution for means is equal to the mean of the population, right? And we had this formula for standard deviation where we would take the standard deviation of the population and divide it by the square root of the sample size, right? And then to find probabilities, we would calculate a z-score, right? We would do the sample mean minus the population mean, or the parameter, divided by this new standard deviation that we have to calculate, right? And in proportion problems, right, we were very easily able to calculate a standard deviation if it wasn't given to us, right? We had a formula for that, right? So remember these, right? P1 minus P over N, all underneath the square root, okay? So that's how we would find the standard deviation for a proportion, right? For a sampling distribution of proportions, okay? But this is honestly much harder to do with means, right? Just in general and in real life, like with real like work that statisticians do. This is a difficult thing to calculate, right? Like the population standard deviation is difficult to come by, right? Which, if you remember when we were talking about sampling distributions, right, you have to know the standard deviation of the population in order to find the standard deviation of the sampling distribution, right? That was necessary. I told you had to know that in order to calculate your probability, and you couldn't do the problem without that information, okay? Which is true, right? You can't actually figure out what those sampling distributions look like without that piece of information. But that piece of information is very difficult to come by in the real world, okay? It's very often that we don't actually know the population standard deviation when we're dealing with means, okay? So what that means is that we have to use the next best thing, which is the sample standard deviation, which, if you recall, okay, population standard deviation is notated here with this Greek symbol, right? But SX is your standard deviation of the not of the population, but of the sample, okay? Now, here's the kicker though. Once you replace the population standard deviation with the sample standard deviation, you're not actually calculating a z-score anymore. You're not actually calculating a z-score. You're calculating something else, okay? And that's where this thing called the t-distribution comes in, okay? This was one of the greatest discoveries in statistics because it allowed us to do so much more and apply our knowledge of normal curves to so many more scenarios, right? This t-distribution was like a major thing in statistics when it first came around. And in class, I'll tell you the story of how this came into being, okay? So when we use the sample standard error, right? Right, you've heard me call it standard deviation, standard error, right? Remember, they essentially mean the same thing. Technically, it's standard error when we're talking about a sample, okay? But when you don't know the population standard deviation and you have to use the sample standard error instead, okay, we use a t-distribution in a T curve instead of a Z distribution with the Z curve, okay? The T distribution is exactly the same shape as the Z distribution, so it looks like a normal curve, but it has more area in the tails. Okay, so that's the only real difference, right? So same shape as the Z distribution, but it has more area in the tails. But you can kind of see if you look at this diagram right here. Okay, so remember your standard normal curve, which is where all of those z-scores come from, right, usually can be contained from about like -3 to +3. That's where most of that data lies, right? The T distribution, which you can see kind of up here at the top, is the same shape, right? It still looks like a bell curve. It's just there's a bunch more area and a little bit more data further out. So there's more area in the tails, okay? Just like a normal curve, it's symmetric with a single peak at 0, okay? So basically, you just have a much larger spread than the normal curve, okay? Another really, really important property of T distributions is that there is a different T distribution for every possible sample size, okay? Which is a little bit weird to think about, right? But if you think about some of the problems that we've done in the past, right? I've told you that the higher the sample size is, usually the more accurate you can get your data. This is another one of those like scenarios, right? So the T distribution, which you can see a little bit better, and I'm actually going to zoom in here on the right-hand side on this little graph right here, because I don't have it on the slide. Okay, so what you see here on the right side of your screen is multiple different T distributions. Okay, the purple line here is the standard normal curve, right? A T distribution with a smaller sample size is this little red dashed line here, right? So still looks like a normal curve. It's just it has more area in the tails, right? There's more space here in the tails, right? As we increase the sample size, right? So this kind of like bluish green line in the middle is getting closer and closer to that standard normal curve, right? So the higher the sample size, the closer the T distribution is to the standard normal curve, okay? So then the question becomes, all right, well, great. How do we then figure out which T distribution to use, right? So the way that we do that, okay, the distribution that we use is determined by something called the degrees of freedom, okay? And the formula for the degrees of freedom is as you can see on the screen, the most complicated stats formula that there is, okay? So the degrees of freedom, the way you calculate degrees of freedom, which is usually abbreviated DF, it's the sample size n minus 1. Okay, so sample size minus 1. Okay, so if my sample size is 15, the degrees of freedom would be 14. Okay, and like I talked about already, as the degrees of freedom increases, the shape of the T distribution becomes more and more and more like the standard normal curve. Okay, right? The formula to calculate a T value, so not like a Z value or a Z score, but a T value or a T score, okay, is basically the same as a Z score. So it's T instead of Z equals, so it's still X bar minus mu, so that doesn't change, divided by the only change here is that you're replacing the population standard deviation with the sample standard error. Okay, so this right here is the only change, right? You're still doing statistic minus parameter divided by a standard deviation of some kind, okay? All right. So next thing we got to talk about is, because one of the things that we're going to learn about in this section is confidence intervals for means, right? So if you remember when we did confidence intervals for proportions, right, you would have to figure out what one of your critical values was in order to make your interval wide enough to have the stated confidence level that you want to have, okay? So for means, instead of doing a Z star value, right, you are finding a T star value. Still a critical value, but it's T instead of Z, okay? And the way that you find out what your T star value is a little bit different because you're going to use a different table. So just like we have a Z table for our Z values, we have a T table for T values, okay? But honestly, really one of the only things that the T table is good for is figuring out what these critical values are, the T star values, okay? So I'm going to kind of explain how you use the T table, and then I'm going to show you an example and show you what the actual table looks like. Right? So we're going to do one of these questions. I'll kind of show you my an example of what I mean, okay? So the T table is laid out where on the left-hand side, it has a column with a bunch of degrees of freedom listed, okay? And it goes from 1 all the way down to like very large numbers, okay? So what you do when you're reading a T table is you have to find your degrees of freedom on the left, okay? Which, remember, degrees of freedom is sample size minus 1. Okay. If your degrees of freedom is not listed, so say you have like a random slightly large sample, so once you get up into higher numbers, your like higher sample size numbers and thus higher degrees of freedom, your T table is not going to list every single degree of freedom from like 1 to 1,000, right? That's too much, okay? Because once the degrees of freedom gets large enough, the values, the T star values, the critical values, don't change very much from like going, just increasing by like 1, increasing your sample size or your degrees of freedom by 1. It really doesn't change that much. So the table is going to skip a little bit once you get into higher numbers, okay? So if your degrees of freedom is not listed, like it's not on the T table, what you do is you round down to the next closest value, right? Even if it's fairly far away, right? You can't ever round up because if you round up, you're saying essentially that you have more data than you actually do, right? And you're more certain, right? And you have like more accurate data than you actually do, right? So it's better to be safe than sorry, right? So we round down, right? Because we can't assume that we have a larger sample size than we actually do, okay? So degrees of freedom is on the left. You find your confidence level at the bottom, and then you record where those two, where that row and that column intersect, right? And that where they intersect is your T star value, your critical value, okay? So I'm going to do an example for you here. So I'm on page 3 of your notes. I'm going to do the first 2 here, right? And then I'm going to have you try these other the other 3 that are on here, okay? So we're just trying to find the degrees of freedom and the T star value for each of these, okay? So in this first one, I'm dealing with 95% confidence, and my sample size is 12, okay? So if my sample size is 12, my degrees of freedom is 12 minus 1, which is 11, okay? I'm going to now go over to my T table, which looks like this, okay? I'm going to look for my degrees of freedom here on the left, okay? Whoops. Sorry, folks, 1 second. My mouse can be so trigger happy sometimes. Okay, so my degrees of freedom is right here, 11. At the top, it gives you tail probabilities, right? So that's like the leftover after you cut out a certain middle, right? So like if each tail probability is 0.1, that means there's 0.1 here, 0.1 here. So that means there has to be 80% in the middle. So the confidence levels down here, right, at the bottom match with your tail probabilities at the top, right, in order to make like 100% total, right? Okay, so here I know I want a 95% confidence, which is this column here. Okay, so what I'm going to do is basically say, all right, where do those intersect? So I have 11 as my degrees of freedom right here. Okay, and you can kind of see that as my confidence level goes up, because my highest confidence level is on the right, okay, the T star values keep getting larger, right? Which makes sense, right? Because if you want to fit more data, you have to give yourself more space, right? So you need your critical value to be larger. It's the same as your Z star values, okay? So I also have here 95% confidence. Okay, so where those two intersect is this value right here, 2.201. So that would be my T star value. So my T star value is 2.201. Okay. All right, I'm going to do one more, and then I'm going to have you guys pause the video and try this for yourself. So this one says I'm dealing with a 90% confidence interval, and my sample size is 48. So that means my degrees of freedom is 48 minus 1, which is 47, and I'm dealing with 90% confidence. So I'm going to go back to my T table. Okay, I'm going to look on the side here for 47, which doesn't exist. See how as I get into larger degrees of freedom, there's a lot of skipping that goes on, okay? So I'm going to round down to my next nearest choice. So if my degrees of freedom is 47, then that means I'm going to round down to 40. So this would be my row that I was looking at here. Okay, and then I wanted a 90% confidence, I believe, if I remember that right. Yes, a 90% confidence. So here's my 90% confidence, and I'm not going to circle the whole thing because I can already kind of see where these intersect. So those intersect right here at 1.684. So that would be my T star value. Okay, so my T star, my critical value here is 1.684. Okay. One other thing I want to point out to you about the T table as, or before you all try the last three here, is that, and I can't zoom in on this anymore, unfortunately, but what I'm hoping you can kind of see is that as these degrees of freedom get larger, so it goes to 80, 100, 1,000, and then eventually you have infinity down here. So the infinity is essentially like your Z table, right? Because remember I told you that the larger your sample size is, the closer your T distribution will get to the shape of your Z distribution, the normal distribution. So if you look down here, okay, if you remember, like the Z star value for 95% is 1.96, and there it is. Right? The Z star value for 99% confidence is 2.58 usually. We round up, right? And there it is, right? For 95 or for 90% confidence, it's 1.6 4 or 1.65 technically, if you round, right? So if you ever forget any of your Z values, you can find a lot of the common ones here on this table. Okay, another thing I want you to notice is if you look going from 1,000 to infinity, these values don't change very much, right? So like here at 90% confidence, it goes from 1.646 to 1.645. So like it barely changes, right? Most of the change, right, and the rapid change happens here when you have really small sample sizes, right? Like here for 95% confidence, going from a degree of freedom of 1 to 2, it goes from 12.7 to 4.3. Right? So most of the rapid change happens here, right? And I'm hoping that like intuitively it kind of makes sense why these numbers are larger if you have a smaller degrees of freedom, because you have a smaller sample size, right? And we usually are less certain about our results when we have smaller sample sizes, right? So when constructing our confidence intervals, we have to make sure that we give ourselves a wide enough range in order to truly capture the true value, right? The true mean, whatever it is in the context of that problem. So the smaller the sample size, right, you have to give yourself a much wider berth, basically, and make your interval much larger, which is exactly what the critical value does, right? That's the whole point of having it, okay? So what I'd love for you all to do is pause the video and try these last 3 out using the t-table, and which, by the way, you can find in Canvas under the helpful formulas, like where you find the formula sheet and the Z table, all that stuff, you can find it there. So give those 3 a try and then check back with me to see how you did. All right, folks, go ahead and check your answers against mine. So for the third one, I have a degrees of freedom of 9 and my t-star value was 1.833. For number 4, I have a degrees of freedom of 94, which is not on my t-table. So I had to round down to the next closest number, which was 80 on the t-table. And I got t-star equals 2.639. Okay, and then for number 5, I'm dealing with 99% confidence and n equals 4. So my degrees of freedom is 3, and my t-star value is 5.841. And then it asked, how does this compare for the z-star value for the 99% confidence interval? So the z-star value is 2.576, so obviously the t-star value is much larger, right? And I wrote out the reason why, right? Just as a little reminder / summary for you, because that sample size is so small that you end up with a lot more area in the tails, all right? Okay, so the last thing that I need to talk to you about in this video is the conditions that allow us to use a t-distribution, okay? And shocker, 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 I know, you're shocked and amazed. It's those same 3 conditions that have been showing up since the beginning of the semester. Same conditions: randomness, 10%, and success fail. So I told you you'd get sick of them. Are you sick of these conditions yet? Okay. The only difference, okay, which you hopefully remember from when we did sampling distributions of means, is that for the success fail condition, okay, for success fail, for means, you don't have to do NP, N1 minus P, right? All you have to check is that N is greater than or equal to 30, or that the population shape is normal. Okay, so as you saw from when we were calculating some of these t-star values, that sometimes we're getting sample sizes that are much less than 30, right? Like we had some sample sizes of 4, 10, 12, right? Much smaller than 30, okay? And with problems for means, oftentimes the population shape is unknown, right? So this condition, the success-fail condition right here, becomes much more difficult to check, okay? But we can still use and go forward with our confidence interval or our hypothesis test, even if the sample size is less than 30, okay? If you graph the sample data to get an idea if there's any major outliers or skew. Okay, so if you do a quick graph of the sample data and it doesn't look like obvious outliers or skew, you can keep going with the problem even if the sample size is small or less than 30 and you don't know the population, the shape of the population. Okay, so the best way that I have to summarize this is telling you when you can't, absolutely cannot use a t-distribution. Okay, you cannot use a t-distribution if all three of these things are true. Okay, so the sample size is less than 30. That's the first thing that has to be true. The second thing that has to be true is that the population shape is unknown. Okay, and the third thing that must be true is that the sample has skew or outliers. Okay, so these are the conditions, right? All three must be true. Basically to like stop you in your tracks, right? So you can't continue with the problem if all three of those things are true, right? If only two of them are true, you're fine, right? Like you can keep going with the problem, okay? Right? Okay, so the reason that we are allowed to do this, I kind of wrote out for you in this note right here, which says the sample does not have to have a normal distribution, right? That comes from the success-fail condition, okay? Like the sample won't have a normal distribution, right? Because it's a sample, right? But we use the whole point of doing all this inference stuff, like constructing confidence intervals and running hypothesis tests, is to use sample data to be able to make an inference about a population. So we use the sample data to make an inference about the shape of the population distribution. So we can safely assume if the graph of the sample data doesn't look skewed or doesn't have like very obvious outliers, then we can assume that it came from a normal population. Okay, so very similar to the last one, I'm going to do the first two on here to determine if we can use a t-star value here or not, like if we can use the t-distribution and why. Okay, so and then I'm going to have you try the other two. So the first one gives us this stem plot right here, okay, and they're telling us that it's a random sample of 20. Okay, so the first thing I got to check is my sample size. So n is 20, which is less than 30. Okay, so that's a problem, right? So I have to check my data, right? So if you look at this data, right, and kind of flip it on its side, it kind of looks like this. So this is skewed. Okay, so my sample size is less than 30. I don't know the shape of the population, and my sample has skew, right? So we can't use t-star because you have both of these things, a skew and my sample size is less than 30. Okay, all right. So this second one, I have a very similar issue. Okay, so I only have 5 randomly selected visits to a coffee shop. So n is 5 here, very obviously less than 30. I don't know the population, and again, there's a very obvious outlier right here. Okay, so again, we can't use T star here because we have these two things. My sample size is too small, and I have a very obvious outlier. Okay, so I want you all to try out part C and part D, okay, and then check back with me to see how you did. All right, y'all. So for part C here, they told us we're dealing with a box plot of 100 randomly selected students. So because my sample size is greater than or equal to 30, I'm golden. I don't have to check anything else, right? So even though that distribution has outliers in it, right? It has two outliers here and here, right? It doesn't matter, right? Because my sample size is greater than 30, right? So I can use T star, okay? And then for D, you may have gotten a slightly different answer than I did, okay? Just because some people may have looked at that data and said that looks skewed, okay? So here we're dealing with a random sample of 20 students. So my sample size is too small. It's less than 30, and my population shape is unknown. But the sample here has no obvious outliers, like blatantly obvious or extreme skew. So there's like a tiny, maybe a tiny, tiny, tiny little bit of skew here. Like it's skewed slightly to the right, but in order to not use a T distribution, your skew has to be pretty extreme, like the skew up here in this first example, okay? So because there's no obvious outliers and no extreme skew, we can use T star. All right, folks. So I know this was a slightly longer video. The next ones will be a little bit shorter because I'm just going to talk about the differences between confidence intervals for and hypothesis tests for means versus proportions. Right? But I'm hoping that after watching this video, you have like a clear idea of what T star is, what that T distribution is, and how to determine if we are able to use it. So whichever video you watch next, I'll see you in the next one. Bye, everybody.